Welcome back to our AP Calculus notes. Today we're talking about 3.7 rates of change in the sciences. Things that you need to know. You need to know that if f of x is your position function, then f prime of x is going to be your velocity, f double prime is going to be your acceleration, and f triple prime is going to be your jerk. So what I get from here is my function, my position function, s, which is f of t. If I want to find the velocity, all I got to do is take my derivative, which is f prime, which is 3t squared minus 12t plus 9. So there's my velocity. If I want the velocity after 2 seconds, then what I'm going to have to do is just plug in a 2. So f prime of 2 or f prime of 4 for 4 seconds. If I plug these into a calculator, I should get f prime of 2 is 3 meters per second. F prime of 4 is going to be 9 meters per second. So when is it at rest? That's saying when is velocity equal to 0. So I want to know when is my velocity function up here equal to 0. You could also graph it and find the zeros. That's another option. So if you graph it, you take your velocity function, which was where is it? F of x, this would be f prime of x, equals, what was this? 3t squared minus 6t plus 9. Or not minus 16, minus 12t. T plus 9. There's my velocity. I want to know when is it at rest. Or I guess I can't do f prime. I can do f of x. I can find my zeros. It's at rest at 1 second and at 3 seconds. That's when the velocity is 0, at 1 second and at 3 seconds. So at x equals 1 and at x equals 3, the velocity is at 0. When is it moving forward? Well, that's when my function is above 0. My velocity is above 0. It's positive if it's moving forward. So from 0 to 1, it's above that x-axis, and from 3 to infinity, it's above that x-axis. So I could say from 0 to 1, or from 3 to infinity. It should be moving forward. If I want to sketch a diagram, then what I'm looking at for this diagram is I've got this thing that's moving forward from 0 to 1. So it's moving forward, and then it moves back, and then it moves forward again. So it moves forward, it moves backward, and then it moves forward again. All right, finding that total distance traveled. If I need to find the total distance traveled by that particle in the first 5 seconds, I can find, using my velocity function, distance, because distance is rate times time. So what I have for this distance traveled during the first 5 seconds, let's say from time 0 to time 1. Well, I could also just find the position. We could do that too. So from time 0 to time 1, we're moving forward. So at time 0, I'm at, where's my, at time 0, if my S of t is t cubed minus 6t squared plus 9t, at time 0, I'm at 0. At time 1, I'm at, let's see, it's 1 minus 6, I'm at 4. So from second 0 to second 1, I go 4 meters, or 4 units. So I went 4 units, maybe I'll say 4 meters. I can do the same thing using my position function to go from 1 to 2. So time 1, I'm at 4. At time 2, let's see, that's 8 minus, oh, I gotta do some math here. 8 minus 24 plus 18, I'm at 2. So I went 2 meters in the wrong direction. I went 2 meters backward. So I went 4 meters forward, then I went 2 meters backward. At time 3, let's see, time 3, that's 27 minus 54 plus 27. I'm back at 0, so I went another 2 meters to the left. So I went 4 meters to the right, 2 meters to the left, 2 meters to the left. At time 4, I'm at 4 again. So I went 4 meters. And then at time 5, let's see, 5 cubed minus 6 times 25 plus 45, I'm at 20. So I went 4 meters to the right, then I went 4 meters left, I'm sorry, I'm at 20. That was almost a mistake. At time 5, I'm at 20, so I went 16. So I went 4 meters to the right, 4 meters to the left, 4 meters to the right again, then 16. If I add all these up, I get 28 total meters traveled. All right, and our acceleration if position is t cubed minus 6t squared plus 9t, and velocity is 3t squared minus 12t plus 9, then acceleration is going to be 6t minus 12. So then a of 4 is 6t minus 12, which is going to be 12 meters per second squared. All right, I'm going to ask you to graph your position, velocity, and acceleration functions on Desmos, and then just sketch a graph of what you see on your paper or on your graphing calculator if you don't want to use Desmos. Speeding up, slowing down, that's acceleration greater than 0, and this is acceleration less than 0. So graph that acceleration function that we found over here, the 6t minus 12, graph that, and then see when is it speeding up, when is it slowing down. And you should get, if x is between 0 and 2, it should be slowing down. And if x is greater than 2, it should be speeding up. 6x minus 12, yeah. All right, here's where it gets a little bit tricky. If a rod or a piece of wire is homogeneous, then its linear density is uniform and is defined as the mass per unit length and measured in kilograms per meter. Suppose, however, that the rod is not homogeneous, but that its mass measured from its left endpoint to a point x is this mass function. Mass is f of x. In this case, the average density is the average rate of change. Well, hold on. Average rate of change. That's a fancy way of saying slope. That's a fancy way of saying the derivative. And its linear density is the limit of those average densities, limit of the slopes. So the linear density is the limit as h approaches 0 of these average densities, f of x plus h minus f of x all over h. But we know what this is. We've seen it before. That's just a derivative. So the linear density is going to be f prime, which is 1 over 2 root x. So if I want the average density, is going to be calculated as f of 1.2 minus f of 1 all over 0.2. That's my average density, which ends up being like 0.48. But the linear density at x equals 1, that's when we use f prime of 1, which is 1 over 2 root 1, which is 1/2. Maybe I should label that as kilograms per meter. And this should be kilograms per meter. All right, current, same idea. We see average rate of change of the net charge. Well, that just means derivative. And again, same thing, we see the current is the limit of these average rates of changes. So what I need to find Q prime. 3t squared minus 4t plus 6. So if I want current, I want 3t squared minus 4t plus 6, which is going to be 4.75. That's amps. If I want the current to time is 1, it's just 3t squared minus 4t plus 6, which is 5 amps. And when is the current lowest? We need to graph this function. We need to graph this function right here. 3t squared minus 4t plus 6. So we graph it. 3t squared minus 4t plus 6. And we find its minimum at x equals 0.6 repeating. All right, we'll talk about the rest of this tomorrow, but that's the start of it. I will see you then.